Hi, my name is Nathan Pacey, and today I'm going to be going over random walks on a network, or the impacts of random diffusion processes in a non-spatial domain. So to start off, normally we look at randomness and diffusion in spatial domains like particles diffusing over time. In this project, we looked at a network, or a graph, where each node can be thought of as a person passing on a box to another node, where the connections themselves are defined by friendships. Now, this also means that the random walk is the pathway of passing that box to the next one with randomness involved. So in order to understand the probability of each person getting the box over time, we had to define some mathematics and understand this probability distribution. So to start off, we have the adjacency matrix A, where if a node is friends with another node, the value is 1, and if not, the value is 0. This leads us to a probability where we have the adjacency matrix over the number of connections a node has times the previous probability distribution. Now, when we take this time towards infinity, we notice that it comes to a steady state solution or an equilibrium. And this equilibrium tells us the probability of that final node receiving that box. So there's also some impacts of the graph Laplacian, which is defined as D minus the adjacency matrix, where D is the diagonalized number of connections from each node. So we can actually redefine our probability as the discrete time Markov chain using DNA. So to start off, I defined the graph structure using Python and visualized it with Matplotlib and networks. So to understand how this graph was connected, I looked at the node degree, or the number of connections from each node, and where they were located in the visualization. So this helps me understand which nodes have the most friends, which have the least, and kind of where they're connected to in the graph itself. So next I used the Markov chain and did a loop over time where I had a specific threshold that defined the steady state. So in this case, I used the threshold as a percentage where I looked at the previous Markov chain probability and the current one, and if they were within the threshold, I said that was forming steady state, or it was at the equilibrium, and if it was outside of that threshold, to keep iterating. So this leads us to the steady state probability over time. And we can see that for a single node with a small threshold of about 1%, we can see that there's a strong correlation between the steady state probabilities and the node degrees. As well, when we increase that threshold, we can see that there's less of a correlation, or there's more differences from the starting node to which node has the most probabilities at the end. Specifically, you can think about this like if I started at node 1 and node 1 is not friends with node 12 directly, there's a lower chance that node 12, even if it's more connected, is going to receive the box when we start at node 1. But if we iterate enough throughout time, node 12 is going to be the highest steady state probability. So this is exactly what happened for node 34. Regardless of which node we start at, when we continue the Markov chain over time, which is the same as reducing that threshold to 0, we could see that the highest probability was for node 34, regardless of where we started. So we also wanted to look at the structure of the graphs using this graph Laplacian. Specifically, we wanted to take the second eigenvalue and vector of the Laplacian, which is defined as our Fielder vector. Now, Fielder vectors are used in spectral graph theory to understand which clusters of a graph we can allocate. So specifically, I took the Fielder values of each node and plotted the positive and negative ones separately. And you can see that this distribution, or this visualization, represents our graph pretty well. We can see that nodes of a positive Fielder vector are connected pretty internally, as well as nodes with a negative Fielder vector are connected internally. Now, this has impacts to the steady state probability, or the probability that a node will receive that box at the end of our random walk. So for negative nodes, we can actually see that node 1 for a larger threshold is the most likely to receive the box at the end of the random walk. Well, for positive nodes, even for a large threshold, it doesn't change. 34 is still the node with the largest probability distribution of receiving that box. And this makes perfect sense when we go back and we look at these two clusters. Node 34 is highly connected within the positive fielder vector nodes, while node 1 is highly connected within the negative fielder vector nodes. So it makes sense that we see this discrete difference. Now, this difference is not just present when we have a high threshold, it's also present when we have our steady state or a very low threshold. So when we look at our low threshold and we look at the probability distribution at node 1, we see that the negative fielder vectors have a distinct higher probability of giving node 1 that box at the end of the random walk compared to the positive fielder vector nodes. And the reverse is true for the probability at node 34. So to summarize, we used our Markov chain and we iterated for thresholds that approach 0, and we converged to a single steady state solution that was directly proportional to the number of connections each node has. Now, this makes sense because if you have a lot of friends and your friends are all connected in a graph, if you continue throughout time, the person with the most friends is probably going to receive that present. However, if you don't iterate for many times, it's going to depend on where you started. So this is exactly what we showed with our probability distributions. As well, we used the Laplacian and its subsequent fielder vectors to show that there's two distinct clusters within this graph, each of which have distinct properties, distinct internal connections or algebraic connections. And we could see how those connections affected the probability distribution for both high thresholds, which actually changed the highest probability distribution from 1 for negative nodes to 34 for positive fielder vector nodes. But it also impacted when we have a steady state solution with the threshold going to 0, as we saw that negative nodes still had a much higher probability of giving the box to node 1, while as positive nodes had lesser. And conversely for 34, node 34. So this gives us the suggestion that if you don't want the present, you definitely shouldn't connect with node 34 as it's the most highly connected, and after our steady state is reached, the probability is the highest as expected. However, if you're already friends with nodes in the negative fielder vector cluster, you should probably not connect with node 1 if you don't want that present. And the reverse is true if you do want the present. But if you can only connect with one node and you don't want the present, connecting to a node that's not very connected, like 12, makes a lot of sense. So to extend this a little bit, we could look at subclusters. What happens if we iterate and identify subclusters within the graph? What happens when we say that a friend has to be added to this network, but it can connect to 2 different nodes and 2 only? There's going to be different dynamics we can explore that will tell us more about the graph and the analysis of actually what goes on within it and the connectivities of it, which are highly relevant to not only the mathematics and physics that we've explored here, but also to computer science problems like social media and Google Map type searches that are specifically relevant to graph theory. So thank you very much, and that concludes my presentation.